for the first chapter, this is the last point I'm going to take for first chapter. So after this, the chapter 1 will end and we will start chapter 2 from next lecture. So I will try to finish this part in today's lecture itself. Okay, so in earlier lectures I have told that there is a Fourier transform. Okay, so when we have to transfer or transform the wave function from position coordinate to momentum coordinate or the case wave vector. Okay, but we know how to write this. P is equal to H cross into K. Okay, so K and P are related to each other, right? So therefore I can write them in K form or P form. Okay, in both form I can write this. And if I have to do reverse, that is for K part I have to write, then we take the inverse Fourier transform. So what is difference in between equation number 114 and 115? That you can see here exponential of ikx and here it is minus ikx. Okay, so in Fourier transform the limit is not going to change, limit is from minus infinity to plus infinity, but this exponential part, this is here ikx, here it is minus ikx. Now again, if I told there is a relation between K and P, so if I have to write this equation instead of K I have to write in P. So how it will change? We have seen that K is equal to P upon H cross or P is equal to H cross K, right? I just wrote down here, P is equal to H cross K. So what will be the K? K is equal to P upon H cross, right? And not only P or K, we have to write the differentiation. There is dk here in the equation, you can see here is the dk, right? So we take derivative on both sides, so we will get dk is equal to dp upon h cross, right? So we will substitute this in the above equations and then we can get this equation. Okay, so in this equation put, instead of K put P upon H cross, so here you can get P upon H cross, and instead of dk you have to write dp upon H cross. Okay, so there is one H cross here, but it is in square root. Okay, because this is equal to actually H cross, but we have splitted this into root H and root H here because here is no dk, so here is directly dx, but for mathematical purpose we have splitted this root H cross here and root H cross here. Okay, so you can remember these things, you can remember this part, and when we have to take transpose, just instead of ikx you write minus ikx. Okay, or instead of ipx by h cross you write minus ipx by h cross. So equation 114 and 116 are called as Fourier transform, and 115 and 117 are called as a inverse Fourier transform. Okay, then what we have to do, here you can see there is a notation or there is point probability density. So what is probability density? We have just seen psi star psi, we call as a probability density. So we have to take psi star into psi. So from equation number 114 or from 116 we can write the equation for psi star and psi. Okay, so when we have to take psi, okay, we can take this as it is, and when we have to take psi star there will be reciprocal of this. Okay, not reciprocal, complex conjugate of this. So we have taken in P notation. So psi becomes psi star, psi becomes psi star, phi become phi star, and ipx become minus ipx, right? This is phi star and this is phi. Okay, now you can see here there are two different notations, here is P and here is P dash. Why we have done this separately? Because this is operating on two different times it is operating. So to distinguish between this integration and this integration we have written P dash. this is also exactly equal to p. Okay, but we have to do this 2 times, so this is not square. Okay, so we cannot square this or we cannot cancel this, because we have to first take integration of this and then multiply the number to this, and then we take again the integration. Okay, so this is, therefore this is notation is different. Now what we have done, we have changed the order of integration. So in mathematical part you can see we write double integration and there is some function, and then we take dx and dy. Okay, so now what we can do, if the function can be separated into x part and y part, then we can do integration of dx part first, whatever the function is there with dx, into we can do integration of dy. So we will separate the y part and x part. So we can do this first and then this, or we can do this first and then this, right? So this can be done. So we know we can change the order of integration. So the same process we have done here. So instead of p, we have taken x part first. So in integration what we do, we take from right hand side, right? We solve from right side. So here dx is on the left side, so this means we have to solve this at the end. We have to solve this first, then this integration, and then this. But what we have done, we have changed this order of integration and we have solved for dx first. Okay, so what are the parts where you can see this is coming from, one part is from this, e raised to I px is from here, and I p dash x upon h cross is from here. Okay, so when I have taken all together, okay, I will write down exponential of minus I, okay, I will write k in p upon h cross, I will write k x. Okay, this is under one integration, and then there is another integration, there is e raised to plus I k dash. Okay, so this is k dash means p dash upon h cross and x, right? So when I have taken I have changed the order, what I can do, I can take them together. So this will become under integration, obviously there are 3 integrations total. I k dash minus k, okay, k dash minus k into x. So for exponential we add the exponentials when there is product of exponentials. So the same process they have done here. So where is that? So therefore we can see p dash minus p dash minus p, and this is I h cross is common, x is common. Now we have to use one definition of Kronecker delta. So exponential of e raised to I will write in k minus k dash, or okay, I will write in x form, x minus x dash, or h dash minus x. It does not change this over dx. This is equal to delta x, x minus x dash. So what does this mean? What is the Kronecker delta? We generally write what? This. Okay, Kronecker delta is delta I z. Okay, so Kronecker delta means if I is equal to z, then my answer is equal to 1. Okay, so this is equal to 1 if I is equal to z. This is we call as a Kronecker delta. Otherwise, if this is not equal to, if I is not equal to z, then this is equal to 0. This is we call as a Kronecker delta. But here is no IJ symbol is there. So this is not a Kronecker delta symbol. This is called as a Dirac delta. I will type. This is called as a Dirac delta. This is what? This is Kronecker delta. Kronecker K capital. Okay. So this is Kronecker delta. This is Dirac delta. So how we write Dirac delta? So this is equal to, you can write down in your notebook also. This is equal to, again it has two values. This is equal to infinity if x is equal to x dash. If x is equal to x dash. And this is equal to 0 if these two are not equal. So what is difference? Here it is when they are equal, then it is 1, and here it is infinity. So when you plot the graph of Kronecker delta, Dirac delta, you will get one such spike. There should not be any width here, but practically it has some width. But what does this mean? So only at x equal to x0, so or x naught, x dash, at only x equal to x dash, this has value infinity. So this goes to infinity. I'm just drawing finite, but it goes to infinity, and all other cases the value of the function is equal to 0 everywhere else. Only at x equal to x0 the function is infinity. Okay, so this is definition, right? This is the definition of Dirac delta. So what diagram it is? So everywhere else it is 0, only at x equal to x dash. So this is x dash. So only at x dash the value becomes infinity. So that is our Dirac delta. And we have to use one condition or property of Dirac delta. Okay, what if x dash is equal to 0? If x dash is equal to 0, I can write this as delta of x. So this means the value is equal to infinity if x equal to 0. X dash is 0. Okay, so if x dash is 0, then this reduces to delta x. So when x is equal to 0, then the value of function is infinity, otherwise it is 0. So we have one property, so I am directly using here kx is equal to 1 upon k. You can use c. K is any constant. Okay, delta of x. So what does this mean? It can be x minus x dash. So we have multiplied by k. Okay, so if this function is multiplied by k, then the Dirac delta is changing by 1 upon k. Okay, so this is just property, you have to remember. I'm not going to prove this. And there is one more property. Okay, I will discuss this also. From minus infinity to plus infinity, if we take the integration of this delta x minus x dash, I will write in general x minus x dash, this is equal to 1 over dx. So this means what is integration? Integration is nothing but the area under the curve. So area under the curve is 1 for Dirac delta function. So therefore I earlier also I told you that there are two kinds of delta, Kronecker delta and Dirac delta. So don't confuse with these two. These two are just notations to reduce our mathematical part. So when there are two this can be ij or mn or xy, this can be anything. These are just dummy variables. So if you see such kind of thing, then this is called as Kronecker delta. So this means 1 or 0. But if there is no such thing, but there are some function in the bracket, function of x, then this is called as a this is infinity or 0. Okay, so we have to use these two properties in this derivation. Okay, you can see exponential of I p dash minus p x will become what? Delta of p dash minus p. But why h cross is multiplied here? Because it is in denominator here. So we have used this property, right? So here x is k is in the denominator, or h cross there is in the denominator. So 1 upon h. So this will become h cross in numerator. Okay. So you can get this. You just use these two properties. Okay. You can solve this by yourself. So we are using this property for delta. So f from minus infinity to plus infinity, there is one function of x, f of, let's say, x, and into instead of h dash I will write a. So a is some point x minus a dx. So if such integration is there, then this is equal to f of a. Why is it so? Because anywhere else, if x is not equal to a, this part is equal to 0. So okay, so here it is a and all part is equal to 0. So f of x into 0, f of x into 0, f of x into 0. Here only f of x into 1. Okay, or there is some non-zero part. So at what? X equal to a. So this is f of a. Again other part is 0. Integration is what? We are adding over all the region. So this is only non-zero if x is equal to a. Therefore f of a is the answer of this. Okay. So write this property also. This is also important. This is also important for your net gate exams. Dirac delta function. You get one question on this part. So we have used this property also here. So you can see p dash is cancelled from here. You can directly get here psi of p. Okay. So if this is in integration, so all part here must be equal to psi of p, because when p dash is equal to p, then only this is non-zero, and this h cross is anyway constant, so we can take this outside, and here is already 1 upon h there. So this h cross and h cross get cancelled. Okay. So what we get here from this part, we get psi of p. Why psi of p? Because this is non-zero only when p dash is equal to p, because of this delta function, Dirac delta function. So we directly put, like we put f of x is equal to f of a. Okay. So a is here p. The function was x there and constant was a. Here function is p dash. So this function of p dash, dp dash. A we have p here, and this is instead of x, p dash. So f of x delta x minus a. So we get f of a. So instead of p dash we just write p, and this is just solution. So for all this part we get psi of p, and this function, this integration as it is. Okay, we have not changed this. So you can see where we started from psi dash psi, psi star psi, integration over psi star psi. So this is probability density of wave function in position space, and this is probability density in momentum space. So you can see that this follows that probability current density in momentum representation is also the same. So if our wave function is normalized in position space, then the then the wave function is also normalized in momentum space also. आपण आता एक क्वेश्चन बघितला होता. We have discussed one question in the internal exam, that if space part is normalized, then total function is also normalized. Okay. So if that is normalized, then it is also normalized in momentum space also. Okay. So if the wave function is normalized already, we don't have to again normalize in momentum space. It is already normalized. Okay, so we have to just normalize it once, then we don't have to worry about the normalization. Okay, then okay, I will note this down. We don't have to use this derivations. They are just adding pages. So I will write here. Okay, I will type here. This is in position space, and here it is in momentum space. Okay, so what is the case here? In position space we had momentum operator. Okay, I will write only px. Similar we can write py, pz. So this we write minus I h cross dabba by dabba x, right? Or we can also write this as equal to h cross upon I. We have seen this, how to do this. H cross upon I dabba by dabba x. Similarly, we also had x cap. This is equal to x, right? So in case of position space, we just multiply by position. This is just position operator. So position operator is just the multiplication by position, and this is momentum operator. Now in momentum space the case is reverse. Okay, so we write p cap is equal to p in momentum space. So x जगह p आना है, p जगह x आना है. Just this difference you can make. So in momentum space, what will be the x cap? X cap is equivalent to or equal to h cross upon I. Any notation you can either use minus I h cross or this one, h cross upon I. This is upon dabba by dabba px. Okay. So I'm not taking this derivation. You just see the analogy. X is replaced by p and p is replaced by x. Okay, here is also px. Similarly, you can write for px, py, pz. All in all three axes. This is true. So in general, what we used to write for 3 dimension, we used to write this is equal to h. Okay, minus I h cross and del. So this is what dabba by dabba x plus dabba by dabba y plus dabba by dabba z. Here what we write, this is equal to this I h cross here and del of, okay, in 3 dimension, del of, here we write p symbol. So this means dabba by dabba p x, dabba by dabba py, dabba by dabba pz. Okay, so here it is. I'm not writing this h cross upon I or minus I h cross, so it is there. So this is in 3 dimension, this is in 1 dimension. Here it is in 3 dimension. Okay, I will write in different color. So this is in 3 dimension and this is in 1 dimension. Okay, so this is just analogy and we can see this. There is a derivation they have taken, but we don't need to do this. They have taken expectation value of this. So how we write expectation value for x? So instead of x, we have used the operator I h cross dabba by dabba p. So you can see here for p we just have to multiply with p, right? Okay, x and px we just interchange. Okay, you got the idea. Then we write the equation of motion. So how we can write the equation of motion? In Schrodinger's time dependent equation, or in earlier case what we did in position space, we take the derivative of psi, dabba psi by dabba t, and then we multiply it by I h cross. The same you have to use here. So you can get here this one, psi of p. So take derivative with respect to time, okay, on both side, and then multiply by IH cross. So you will get IH cross dabba by dabba t of phi. Similarly, we used to get dabba psi by dabba t, right? IH cross dabba psi by dabba t. So that will give us the Schrodinger's time dependent equation. Now you can see on the right side, only this part psi of xt is only time dependent, right? This is only space dependent. This does not involve time. So we have to take just derivative of this. So you can see here IH cross multiplied on both side and derivative of only this psi. This is constant, right? Now we can take derivative. Now we know here it is integration over x, right? So instead of time we can try to convert this in the position. Instead of time we convert this into position using the Schrodinger's time dependent equation. What was that? IH cross I dabba by dabba t. So this is total energy operator. So total energy operator, I'm not writing psi here. So total energy operator is equal to what? H cross square, I guess minus H cross square by 2m del square. So this is kinetic energy plus potential energy. So this is total energy. Okay. So we will replace this part by this operators. So this is kinetic energy plus where is this? Kinetic energy plus potential energy, and this is total energy. So instead of this we will write this one, and then we will solve this LHS as it is. Now we will solve this part. V is just multiplication, so we have to solve this part, double derivative of psi, and again here it is also x part. So we have separately solved this integration. So how to solve such type of integration? So this is kind of u into v, right? This is part u, this part v, and integration. So you use by parts, u v over dx, where u and v both are functions of x. So this is equal to u integration of v dx minus integration of u dash, where u dash is the derivative of u with respect to x. I mean this is du by dx into integration of v dx, and this whole integration is dx. Okay, so we will use this definition or this property. We will take this as u and this as v. So why we take this as v? Because we have to integrate this. So we have already derivatives. So first derivative will become psi star, psi dash. ऑलरेडी दोन डेरिव्हेटिव्ह आहेत, त्यावर एक इंटिग्रेशन केलं की काय होईल, हा साय स्टार होईल, आणि इथं काय होईल, हा साय होईल. म्हणून काय केलं आपण, ह्याला व्ही म्हणूयात आणि यू बाहेर आहे तसाच ठेवायचा आहे आपल्याला इथं. सो हा ई रेस्टोचा जो पार्ट आहे तो आपण काय केला, आहे तसाच ठेवला. सो दिस इज फर्स्ट पार्ट. सो दिस इज ओवर मायनस इन्फिनिटी टू प्लस इन्फिनिटी. And again, okay, I will solve this for first and then we will take this integration. Okay, we will show here. So what is going to be here, this part as it is. So this is our u is as it is, and v is integration केला आपण. So integration of this, so one derivative is going to cancel, so dabba psi by dabba x. So ranging from minus infinity to plus infinity. And now what is going to happen, we take the derivative of this. So minus ip upon h cross is there, and okay, minus is there, and minus I k upon h cross, p upon h cross, minus I p upon h cross. So this constant is taken outside, and again this exponential part. and this integration. Okay, so this minus and this minus become plus, therefore you can see here plus ip upon h cross. This is constant taken outside, this derivative, sorry, integration of v, and this is u. Okay, so for this you can see this range is from minus infinity to plus infinity, and we have seen that the wave function vanishes at infinity, so its derivative also vanish. So vanish means it becomes 0. So if this part is 0 at minus infinity and plus infinity, this total part will become 0. So we will ignore this part, this is 0. Now again for this part we will again use this as u and this as v, and again we will solve the integration. Again the first part will become 0 in this, so we will directly write the second part psi dabba psi by dabba x becomes psi, and this part as it is, and again one part is taken outside, constant जो है तो multiply होना है derivative असल्यामुळे, so this will become square. Okay, so instead of this we will put this part, and now the equation, this equation will reduce to this constant as it is, has a constant है, this we will take as it is, this p will become square, here is minus sign, right? So here is minus sign, this h cross and this h cross square will get cancelled, 2m as it is, and this minus I square will become plus. So this is p square upon 2m, then integration of this part. But what is this? You can see from the definition. Okay, we will solve this. Plus v part. This is for kinetic energy part, and this is for potential energy part. Now from the definitions we have seen psi into exponential of minus ipx upon h cross. So this is what? This is phi of p. So for this part we can write phi of p. So you can see directly here. I am not going to see this. So directly we can take p square upon 2m, and this part is already in the integration part in the definition. So this is cancelled. So this is phi p, and this is v. V is constant of p. V only depends on x, and this is now integration on p. Therefore v is constant taken outside, and other part is just phi of p. Okay. So the definition, now you can see this is again same, just like in the case of position space. This is kinetic energy operator, this is total energy operator, and this is potential energy operator. So you can write this as a equation of motion in momentum representation. Okay, so with this the chapter ends here. So you can see the worked out examples. We have also left the part of orthonormalization. I'm going to take that on one day, but we will start the second chapter from tomorrow. Okay.